is Dolores Hill. And yes, and Dolores is really, she's a guest and she's a speaker, but Dolores is also one of our members and has been a member of TAAA for years. She's given a number of really wonderful presentations for us on recent research results in astronomy, and just is a delightful presenter. So I'm sure you will enjoy her. She works also at the Lunar and Planetary Lab on the Osiris-Rex and Bennu projects. So Dolores, are you ready to screen share at this point?
Yes, I think I am. Great, thank you so much. It's wonderful to be here again, and I bring you greetings from the Osiris-Rex mission. I'm very happy to report that in October of 2020, the spacecraft collected a large amount of sample of near-Earth asteroid Bennu, and it will return it to Earth in the year 2023. We expect this to be our country's largest sample return since the Apollo missions that brought back rocks from the moon more than 50 years ago. Today, I'll report on the current status and future plans as well. First, the challenges and obstacles. The mission team passed many milestones in its long journey to study near-Earth asteroid Bennu. It overcame unforeseen obstacles, including numerous house-sized boulders in its path, pandemics, and concerns of sample loss after our successful sample collection. So just to back up a little bit, some of you have seen this slide before, so I'm not going to read the whole thing, but Osiris-Rex is an acronym that describes all of the objectives of our mission. Origins, for understanding the origin of the solar system and organic materials important to life. Spectral interpretation that looks for commercially important materials in the asteroid, as well as trying to understand the composition and thermal properties of the asteroid. Resource identification. Specifically, we were looking for water, and happily we identified it right off the bat as soon as we arrived. Security refers to investigating how asteroids in the main asteroid belt migrate towards the inner solar system to become near-Earth asteroids. And lastly, but most importantly, is Regulus Explorer, to return at least 60 grams of the regolith of asteroid Bennu. And regolith is, again, just our scientific term for dirt on an airless body like the moon or an asteroid, but it's very special dirt. And my spoiler alert is that we think we collected much more than 60 grams of material. I'm delighted to share. All right, so to back up again a little bit, where exactly is Bennu located? Well, its entire orbit is within the orbit of Mars, and that qualifies it to be a potentially hazardous asteroid. Most asteroids are located in the main asteroid belt between Mars and Jupiter. Some belong to collisional families. We think Bennu may be a member of the New Polana or the Euelia families. It's very difficult to distinguish. And again, it orbits the sun in an orbit entirely within the orbit of Mars. And you'll notice it does cross the Earth's orbit in two places, but thankfully not when the Earth was there at the same time. This is what we encountered when we arrived at Bennu. First of all, the shape was just as we expected, right down to the large rock called Ben down in the lower right as it rotates. However, pre-launch thermal inertia models indicated that we should expect smaller rocks than we did find. We learned the models need adjustment, and that's how science works. We make our best understanding, and when we are presented with new information, new data, the models have to be adjusted. The large boulders and rocks challenged the team to locate a suitable sample site. Important discoveries were made all along, and we learned how to navigate in a microgravity environment around the smallest solar system object ever orbited. Indeed, we earned a Guinness world record for that feat, and then we broke our own record. We learned about ground truth comparisons of distant astronomical observations and asteroid materials close up. Dynamic particle ejections from Bennu's surface that have never been seen before, and I'll tell you how those were discovered, and new understanding of rubble pile asteroid formation and history in the solar system. The returned sample will reveal even more important details about its parent asteroid and organic materials important to life. So this is how we collected our sample. We very, very slowly approached the surface. The touch and go sample acquisition mechanism slowly contacted the surface and collected our sample. So we technically did not land. We only contacted the surface for only 5 seconds. Then we placed the sample collecting head into the sample return capsule, stowed the arm, closed the lid, and in May, we'll head back towards home. The original plan was to visually confirm sample collection and then estimate the mass collected by rotating the spacecraft before and afterwards to determine the change in angular momentum. It was a wonderful physics experiment, but you'll see why we needed to change that plan. So this is how the TAG SAM works. It was invented by Lockheed Martin, and this is an early test in what is known as the vomit comet, or an airplane that moves in a parabola, and at the top of the parabola, we get weightlessness for 20 seconds. All we needed was just a few seconds. Here in the box that we created, we demonstrated that we could indeed collect rocks in a low gravity environment. Indeed, almost every time we collected much more than the 60-gram baseline. There are contact pads on the bottom that collected fine particles too, and you'll see those later on, the real ones. So pay close attention to the dust that was stirred up just before the gas fired. That's actually what we saw in the real TAG event. The diagram on the left shows what happens when the high purity nitrogen gas flows through the 15-inch diameter TAG SAM collector. Gas flows out through the mesh while rocks and particles are trapped inside, or at least that was the plan. The ideal sample that we were hoping for, 2 centimeters across, and that's what we did end up collecting. So that's I'll to show, because it's actually more realistic to what occurred. Lockheed Martin conducted more than 800 tests of this device, and this is one that included 10 centimeter or 4-inch rock obstructions. And we showed that even so, we could collect an appropriate amount of sample. It turns out during our TAG event, as the collector contacted the surface, we did indeed touch a large rock, and we think that it was fragile enough that when we contacted it, that it broke apart. So that was kind of an interesting comment on the structural integrity of the rocks. So May 10th, the spacecraft will depart Bennu. And in 2023, as the spacecraft travels past Earth, the sample return capsule will be ejected and it'll arrive at the Utah Test and Training Range west of Salt Lake City. The heat shield will protect the precious sample inside, and the parachute will deploy to make for a softer landing. It'll still be harder than I would like, but it's okay. Our team will be waiting to take it to a special dedicated clean room at NASA's Johnson Space Center in Houston. And that clean room is being completed as we speak. So what did we learn so far? So much more than what's on this slide, but these are some of the highlights that I find interesting. First, we saw that there were boulders up to 60 meters across. Oh my goodness, that presented a huge challenge to our team. There were rock slides, ridges, thermal fractures in all of the rocks, impact craters, evidence of aqueous alteration, amazing geology on this small body. In addition, we discovered from the spectroscopy that there's water locked up in the minerals of the rocks. The 2.7 micron band was detected in the spectra. That water has transformed some of the minerals to phyllosilicates or clays and the mineral magnetite. Bennu, as we expected, is a close match to some meteorites in the laboratory, and yet there are some important differences. And so we're looking forward to seeing the material in the laboratory to conduct many more tests. The sun's radiation on Bennu's black surface actually causes its day to speed up by 1 second per year. Do you believe we were able to measure that? It's pretty amazing. In addition, its position in its orbit changes by 131 feet per day. So over millions and billions of years, that makes a huge difference. In addition, the student instrument, the Rexus, discovered a black hole. That was pretty exciting. And as I mentioned, never before seen particle ejections from the surface of an asteroid were discovered, and we'll look at those shortly. First, here's a picture of that black hole known as Maxi J0637-04. It was confirmed by a Japanese satellite as well, but they definitely caught it in their sights. So they were pretty excited about that. Now I'd like to tell you about the particles that we discovered. They were discovered by mission astronomer Carl Hergenrother totally by accident. Being a good astronomer, he wanted to identify the background stars in the spacecraft's navigation images. Okay. He noticed a star cluster he couldn't quite identify and eventually realized these particles were moving while the camera took the image. He took a ruler and drew a line on these little dashes and realized they converged to a point on Bennu, meaning they were moving very fast and coming from Bennu. This is the first time these sorts of particles have been seen anywhere in the solar system. We now think they could be the result of micrometeoroid collisions with Bennu and or from rocks fracturing and the thermal stresses of daily hot-cold cycles and releasing particles. It could be both mechanisms as well. I should mention that Bennu rotates every 4.5 hours, so it has a pretty fast thermal cycling from -100 to 200 degrees Fahrenheit in that time period. So we wanted to study these particles to find out if they would pose a risk to the spacecraft and to understand them better. It turns out particles are 1 to 10 centimeters across. They're ejected at speeds of 0.05 to 3 meters per second. Bennu's escape velocity is 3 meters per second. So this means that some particles fall back to the asteroid, some orbit the asteroid and then collide with it, and others are ejected completely out into space. The team followed these trajectories, actually of each particle, and measured their brightness changes to learn more about Bennu's gravitational field. Thankfully, there was no danger to the spacecraft. Unfortunately, the locations and timings of these events was not predictable. and there was no obvious physical evidence left behind on the surface. It turns out that we collected an embarrassment of riches during the tag event that gives the team more data to understand the nature of these particles. So let's take a little tour of Bennu. It exhibits impact craters that were formed when it collided with other asteroids, very much like craters on the moon are made. The largest one in this red box is 130 meters across, or 426 feet. And it is a significant fraction of Bennu, and perhaps could have disrupted it into many fragments, but didn't. There are regions that contain very large boulders. Even the smallest ones in this image were too large for our 15-inch collector. The arrow is pointing to a 7-meter size rock to give you an idea of the scale. Notice rocks on top of rocks, angular rocks, jumbled rocks where they've been moved in between huge boulders and trapped. And we are very interested in the white rocks. Are they pieces of a different asteroid? Well, I'll tell you ahead of time that we did indeed find materials that we think are part of another asteroid. Very exciting. This is another example of a boulder field. So this would have been a horrible place for our spacecraft to attempt to collect our sample. The red circle is the original 30-meter radius target zone that we needed to be flat, smooth, containing small rock fragments 2 centimeters across, suitable for the tag SAM. You'll notice there's nothing like that in this picture. This would not be a very good sample site. Thankfully, Lockheed Martin Navigation and Flight Dynamics team early on determined that they could accurately maneuver the spacecraft to a circle only 5 meters in radius after all. That's the green circle. So right away, the science team was able to identify many regions that would fit this new criterion. They down selected to a list of Sweet 16, then an Elite 8, and down to final sample sites. Here's some of the boulders that we were interested in. We've identified at least 6 bright boulders containing material that are probably from asteroid 4 Vesta that may have been incorporated into Bennu's parent asteroid before it broke apart and reassembled into smaller rubble pile asteroids like Bennu. There may be other asteroidal materials mixed in the sample too, sort of a 2-for-1 or 3 in the collected sample. I'm really looking forward to the mixture. So now let's fly with the spacecraft over the Nightingale sample site. You'll notice what a difference 3 dimensions make. This movie combined images from the OCAMs, or the Osiris-Rex camera suite, the laser altimetry data from OLA, and the resulting digital terrain model. We used what's known as a natural feature tracking and hazard maps to plan the path for the spacecraft into the site, because we needed to get in and out without any part of the spacecraft touching rocks or boulders safely. So this was essential to a successful tag maneuver. It looks a lot different at this scale than just a 2-dimensional picture, doesn't it? All right. So now let's move on to the tag maneuver itself. So tag stands for Touch and Go Sample Acquisition Mechanism, is the tag SAM. And we're waiting only 15 minutes for the slide, 15 seconds for the slide to change. There actually were 18 minutes one-way communication during this procedure. This picture actually took several hours to complete. Earth received confirmation of successful touchdown on October 20th at 6:08 p.m. Eastern Daylight Time. The sampler head touched Bennu's surface for approximately 6 seconds. And it was much slower than our little movie shows here. After that, the spacecraft performed a back-away burn to a predetermined safe orbital position. And I'm going to show you the end of the collection a little bit slower so that you can see some of the particles that were lofted during this procedure. So here we go. Data show that the collector actually pushed downward into the regolith, perhaps tens of centimeters as it touched, but that the spring in the arm was not triggered. This indicates that the surface was very weak. It's possible that the collector crushed a fragile rock when it contacted the surface. And I'm going to play this again. There we go. Notice all of the particles lofted in the cloud. Some are streaks, which shows how fast they were moving during the exposures. In laboratory tests, this turned out to provide the largest amount of sample. The engineering team is currently completing their TAG reconstruct report from their telemetry and sensors. So one of the ways we were going to determine how much sample we collected was by directly imaging the collector head. On October 22nd, we imaged the TAG SAM head, and it indicated that there was plenty of material. There was material in the Velcro pads around the bottom as well. However, you see those streaks and shadows. Those indicate there was material escaping from the cylinder. Although we collected a huge amount of material, we definitely did not want to lose any. There was a small rock a few centimeters long wedged into the mylar check valve. There's a curved shadow over to the left inside of the collector in the shadow, which is where the rock is located. And it wedged the mylar open so that material was able to escape. A decision, a very difficult decision, was made to forego the mass measurement maneuver. That's the maneuver that we were going to do to rotate the sample arm before and after sample collection to determine how much mass we collected. We didn't want to jostle the sample head any more than we did already, and we didn't want to lose any more material. So a decision was made not to do that maneuver and to go directly to stow as soon as possible without dislodging any more sample. This was a huge challenge for the Lockheed team because they had just experienced very intense operations during the TAG event itself. And then we told them, no, we're not waiting a week. We need to stow the sample right away. So they had to rewrite all of their commands, test them, and prepare to stow the sample much, much earlier than they were planning. And they rose to the occasion. The silver lining in all of this is that we think the collector was actually completely full right after collection. We can see that most of the particles are thin and flaky, just like cornflakes. This provides real data that the astronomy team can feed back into the photometry and the trajectories for those particle events that they were studying. Amazingly enough, they even measured light curves on every tumbling particle. Pretty amazing application. All right, so here's the STOCAM showing the sample return capsule and the TAG SAM head. The engineers monitored every facet of this procedure. They moved the collector a few millimeters at a time. In between, they waited 18 minutes one way light time to find out if their command worked properly and if everything, they were able to confirm their commands. So again, this procedure actually took hours. It was incredible. But there it is, nicely stowed. There are frangibles at the top of that collector that were blown to disconnect the arm from the collector. And then we closed the top of the sample return capsule, and this precious sample is safe and sound. That white portion is the heat shield that will bear all of the brunt of the heat as it comes in through our atmosphere, again, protecting our sample. Ready for return to Earth. It's September 24th, 2023, which will come very soon. The spacecraft will depart Bennu on May 10th. The other thing I'd like to point out in this picture are all of the little dark spots on that sample return capsule. Those are actually particles of Bennu that got lofted when we collected our sample.
Dolores, there's a question that I want to just interrupt you for.
Sure.
The particles, it said, this comes from Ronald Wilcox. He
Okay.
says, did you mean on the particles 1 to 10 millimeters, or because I think you said 10 centimeters, which seems kind of big.
Oh, that were being ejected from Bennu.
I think this was the ones that you collected.
No, the largest rocks we think we collected were 2 centimeters, but we touched down onto a rock that was probably 10 centimeters across, and we think we actually crushed it by just touching it, and that alone told us that the rocks on Bennu are fragile, and that if those had come in through the atmosphere of Earth as a meteorite, they would never have survived. So it's quite possible that Bennu has material that we've never seen before. Pretty exciting. But the particles that were ejected from Bennu that Carl Hergenrother discovered range in size from about 1 centimeter to 10 centimeters. That is true.
All right, thanks.
Did that make sense?
Yes.
Good. All right, so before heading back towards Earth, the team will conduct a final farewell flyby of Bennu at a distance of about 2.4 miles on April 7th, so just this next week. We'll repeat a high-resolution imaging sequence known as Detailed Survey that originally took place in 2019, and we'll collect more data. The purpose is to study changes at the Nightingale sample site from our sample collection procedure. They'll reveal information about the crater size, depth, the strength of the material, the sizes, compositions, rocks, the subsurface material, and any sort of layering as far as depth is concerned, and insight into the sample collection process itself. The engineers are interested in that too. So it'll be fascinating to see what kind of crater we created. Based on what we learned at Bennu, we expect to see rocks and flaky particles like these carbonaceous meteorites, perhaps with some important differences in composition, material strength, porosity, space weathering, thermal inertia properties, isotopes, and more. As the astronomical and remote sensing portion of the mission comes to a close, the sample science teams are ramping up. Sample analysis readiness tests on analog meteorites will ensure the team members are ready to receive the sample, that analytical techniques are refined, and instruments are calibrated, ready to go. Based on testable hypotheses, In 2023, a small portion of the Bennu sample will undergo numerous tests to answer questions about materials in the early solar system, Bennu's origin, hydrothermal processes, space weathering, the nature of organic materials important to life, not life, but important to life, and much more. The University of Arizona's Lunar and Planetary Laboratory will continue to be at the forefront as this mission continues. So I thank you very much and watch for the best of Bennu to come. I'd be happy to take any questions.
Yes, Dolores, we do have some questions.
Okay.
Connor asked, could there also be pockets of non-water ices in Bennu causing the projections?
We don't think so. We did investigate that idea because there were some people who suggested, aha, it's a dead comet. But we were able to determine that there were no pockets of ice or outcrops of ice, that the water is actually locked in the mineral structure, and that there at some point was water that melted and flowed on asteroid Bennu, whether it was while it was on its parent asteroid or not is to be determined. That water is very exciting because there's a huge controversy about where water on the Earth came from, whether it came from comets or asteroids. The isotopic compositions of the oxygen is very different in comets and asteroids. And so we'll be interested to know what it is in asteroid Bennu.
Super.
So we did look for subsurface evidence of subsurface ices, and I did not see any.
Okay. Chris has a question. Was the mass ejection at the terminator as the graphic depicts?
They occurred everywhere. The first one, let's see if we can go back. So the first one shown here, actually we determined was coming from the nighttime side of Bennu. And at first we thought, oh, this is material that suddenly heats up when it hits the sunlight, and there's volatiles in there that cause the rocks to explode and eject this material. Almost as soon as that was suggested, we started to see these things in the sunlit side. So there seemed to be no rhyme or reason to temperature or even type of rock. There are dark rocks and light rocks and smooth and hummocky rocks, and there seemed to be no rhyme or reason. And equally as frustrating, there was no physical evidence that we could see on the surface of these particles. That said, we did mount an astronomical campaign to look for Bennu meteors that might possibly hit the Earth. And it was thought that perhaps 2 or 3 of these could strike the Earth in a certain time period, and that we might be able to detect them. In the end, we did not find any evidence, but we thought it would be interesting if so. So the velocities of these particles are consistent with micrometeoroids striking the surface and ejecting material. They're also consistent with material being ejected as dust and rocks from rocks that fracture suddenly. And so at this point, we don't know for sure which is the dominant process, but amazing. And Carl discovered these because he wanted to identify the constellations and the stars in the background. And he noticed a star cluster that he couldn't identify, couldn't find it in any atlases, and realized, oh my gosh, it's not the background. So, and he had to stretch the contrast on the images. These are actually navigation images that were never meant to be used for any science. And I'm convinced that only Carl could have discovered these because he's such a great astronomer. So,
Great. Thank you.
you're welcome.
Okay, Ed has a question. Is the return container guided when it returns, or does the spacecraft just toss it at the Earth, hoping it lands where expected?
Okay. I understand that the sample return capsule does have some sort of guidance system on it. So my understanding is that the navigation team has to bring the spacecraft as close as it can to the correct trajectory. And then the sample return capsule guidance will take over to refine it, but they still have to be pretty close beforehand. And that's why we're landing at the Utah Test and Training Range, because there's a huge amount of protected airspace there.
Connor has a question.
Okay.
What is the possibility of the sample fragmenting as the capsule goes through re-entry?
Oh, I would say pretty high. If the materials are as fragile as we think, some of those rocks may be vibrated enough so that they will fall apart. That would be very sad, but at the same time, all of our tests can be done on fragments and particles and dust. So whatever form the sample arrives in, we can use. And so I'm actually, personally, I really hope that rock that held open the Mylar check valve survives, because that would be wonderful to be able to slice it and cut it for different kinds of studies. If not, that's okay too. We have a professor here at the Lunar and Planetary Lab who can take a sand-sized grain of sand and get 523,000 samples out of it. So we can use all of these materials. The other thing that we're pretty excited about is that because we are pretty sure we collected far more than 60 grams of material, we may have enough material to be able to do other tests that required a bigger mass that we couldn't do otherwise. So that's all to be determined when we open that capsule and see what's inside.
Okay. A question from Chris.
Mhm.
Any presence of phosphates identified?
I haven't heard any mention of phosphates. There are carbonate materials, there's magnetite, there's phyllosilicates, pyroxenes. I'm not sure about phosphates. Now, that is definitely one thing we'll be looking for when the sample returns to Earth. So, as you know, there are many kinds of analyses that we'll be doing that we can't do remotely, and that are more definitive when you have the sample in hand. Spectroscopy remotely is very difficult because it depends on sun angles, temperatures of the material, a lot of different things. And so in the laboratory, we can control the conditions and add information. So far, I don't think we've seen evidence of phosphates.
A question from Terry.
Mhm.
Would the projected particle process been seen at Vesta or Ceres, or is their gravity such that projections wouldn't escape the surface of those asteroids?
That's a great question. First, no one knew to look for such a thing. And I think that the gravity would dominate. So even if, we know that micrometeoroids strike the surfaces of airless bodies all the time, like Ceres and Vesta, but their escape gravities would be high enough that those particles wouldn't leave the system. Now, once we discovered these particles at Bennu, we immediately contacted the Japanese Hayabusa 2 mission and asked them to look at their images to see if they found anything like this at Ryugu, which is a very similar kind of asteroid to Bennu. They're both carbonaceous asteroids. It turns out that their viewing geometries were not favorable to see these things, but they did look and didn't see anything.
Okay, I had a question for you,
Okay.
and that is, when we left Bennu, did we leave anything from Earth on it?
We don't think so. So yeah, we don't think we left anything behind. We did touch the surface. Let me go to our. All right, that'll get us to the tag event shortly here. We touched the surface, but there's nothing, nothing that should have been left behind as far as contaminating materials, other than the nitrogen gas would have flowed into the rocks. That's really about it. We didn't purposely leave anything behind, no.
Great, that sounds like a really great accomplishment. We have a couple of comments from Facebook. One
Okay.
is the Grand Canyon National Park sends a message that says, thanks for presenting this interesting program.
Oh, thank you.
And Judith Ann on Facebook says, thank you, Dolores, for this fine presentation. It was fascinating. I enjoyed this immensely.
Oh,
So,
thank you so much. I enjoyed it.
well, we appreciate it a lot, Dolores. Thank you so much. So I think
My
that's the
pleasure.
end of our questions and comments at this point. So we will proceed then, Dolores, to our next speaker with
Okay.
the idea that you will hang around and be with us later.
I'd love to. Thanks.
Okay. Okay. Now we have Dr. Mary Turner, our TAAA Master Observer, who graciously every 3 months gives us a report on what's up in the sky. And so she's going to do that tonight. Mary, are you ready to screen share?
Yes, I am. And I'm also ready to turn off my videos because I don't have to look at me. Okay. And let's see, where is the, okay, here we go. And share. Okay, is it showing up okay?
Yes.
Okay, because it seemed to have turned my monitor off, so, or my I'm not seeing I'm not seeing that part of my screen anymore.
Oh,
Okay, so
well, we've got a white screen that starts with objects in the sky on the
okay.
slide, so I think we're okay.
Okay, so this is my semi-normal quarterly presentation, the only difference being because of the other events that we have going on. I was asked to cut myself down a little bit in terms of length. So I know the times are a little in flux, but when you want me to stop, just tell me so. I won't take it overly personally.
We'll be fine, Mary.
Okay, so because we are not meeting in person and are doing these Zoom sessions, and that gives us an opportunity to also share our presentations with Facebook. So I'm going to talk about some things that I talk about a lot because they really are fascinating and enjoyable objects and vary over some different, relatively easy to see, maybe some a little bit more difficult to see, but just some nice things that hopefully you can either go through a telescope live or watch through a telescope online over the next couple of months. These are some really interesting things to look at. Now, Leo itself, of course, doesn't require a telescope. It just requires you to go outside and look up and open your eyes. It will be covering a dominant portion of the sky for a while. Then we'll talk about a couple of galaxies, an open cluster, and a really nice bright star, Regulus, which is also in Leo. So we're going to start by talking a little bit about the lore and legends of the constellation Leo. Leo is Greek for lion. So when we talk about Leo the lion, we're talking about Lion the lion or Leo the Leo, however you want to think about it. It's a rather redundant name, but for some reason, every lion is named Leo, which isn't really giving it a name because Leo is lion. Here is the sort of stick figure we typically see in our constellation programs that indicate the basic shape, the quadrant of the sky associated with that particular constellation. It is right along the ecliptic. It is one of the zodiacal constellations. And here is sort of the image that has been associated with that particular grouping of stars. And I guess it's not too ridiculous, but general picture of Leo. And of course, this is the more artistic representation of the lion. And interesting, it looks, in some ways more like a dog than a lion, but certainly looks nice and calm and peaceful and a rather beautiful looking lion, even though Leo itself is a monster. But we'll get into that in a moment. So Leo, when we go through the mythology, we first see Leo in the saga that are referred to as the 12 Trials of Hercules. Okay, got that out. First trial was for him to bring the hide of the Nemean lion to King Eurystheus. Now, you have to remember that Hercules, since we've done the Hercules legends before, Hercules ended up killing his family. Hercules was the son of Zeus, so he killed members of Zeus's family. And as punishment for this, he was forced to go and perform these 12 ridiculous feats, all of which were designed to kill him. He wasn't supposed to get past the first one, but if he happened to get past the first one, well, then the second was going to get him. If you got back, the likelihood that he was going to get through all 12 was slim to none. So of course he got through them, but he had to start with the Nemean lion. And again, goal of everybody was to get Hercules killed somewhere along the way. So when the king told Hercules to bring him the hide of the lion, Hercules thought he just had to find this lion kill it, skin it, and bring the hide back to the king. The king just happened to neglect to mention to Hercules that the hide of the lion was impervious to man-made weapons. Minor little detail. Might have helped him a little bit if he knew that in advance, but probably not. Hercules, feeling deep regret for killing his family, goes off and hunts the lion, and he does find the lion. He takes his quiver of arrows and keeps shooting it at the lion, but they just bounce off because they're a man-made weapon and they don't work, and the lion not only didn't die, the lion started to get a little bit torqued. I probably would too if somebody kept hitting me with arrows. Now, Hercules had to complete these trials. He doesn't give up overly readily, so he followed the lion into its den. Now, thing is no man-made weapon can kill the lion. But Hercules sort of said, okay, if I can't kill it, maybe I can almost kill it. So he hit it in the head with a club, and he knocked the lion senseless for a little bit. And that gave Hercules time to get very close to him, wrestle him a little bit, and eventually choke him to death. I guess, because Hercules' hands are part of Hercules, so they're not man-made, they're just natural. So natural things, I guess, could kill the lion. Now, of course, the actual task was to return the hide of the animal to the king. But how do you return the hide of the animal if you can't cut it off because it's impervious to any man-made weapons? So his knife isn't going to work. His arrows obviously didn't work before. He realizes that, well, again, just like his hands were not man-made and could strangle the lion, he could now use one of the claws of the lion and drag it around and use that claw to cut off the hide. As someone who has cats, trying to figure out how he would manipulate that claw to cut the whole hide off, I'll leave to your imagination, but that's what the legend says, and we know the Greeks wouldn't lie, right? Right, we all agree the Greeks don't lie. Okay, now, here's a little bit of Hercules. Hercules, although he regretted killing his family, he was still Hercules, and Hercules was, let's just say, rather self-confident. So he did remove the pelt using the claws, as I mentioned, and he did bring the pelt back to King Eurystheus, as was required in the stipulation. But what he realized was the trial said he had to show the pelt to the king. Didn't say anything about giving the pelt to the king. So Hercules shows him the pelt and then keeps it, and then uses it going forward as an impenetrable cloak. If you want to think about it, basically Hercules had the first suit of armor. He could not be injured in any way by man-made weapons. Okay, so the lion itself, is not good. I mean, the reason they wanted Hercules to kill the lion was because the lion was terrorizing the king's country. He was killing people. He was eating all the crops, destroying the farmland. So, typically that's not the type of character or personage or animal that gets a place of honor in the sky. So why do we end up with Leo the lion in the sky, other than as a way to tell us a little bit about the lores of Hercules? It all sort of goes back to Hera. Hercules was the son of Zeus, but not the son of Hera. Now, the parentage of the lion possibly was Typhon, who was maybe the last son of Gaia, the goddess of the earth. And Typhon's wife was Echidna, some combination between a woman and a snake. They were both basically monsters, and all of their children were some form of monster, and one of their children was the Nemean lion. So to protect the lion, Hera sent it to Nemea to live. Purely coincidental that within Nemea was a shrine to Zeus. So Hera made sure that if you wanted to pay homage to Zeus, something that typically most people realized was something that they should do, it's good for their health and well-being, you don't want to get Zeus upset with you, you actually had to get past a very large, very hungry, and almost indestructible lion before you could actually reach the shrine. And I'm sure that was purely coincidental. She wouldn't do that deliberately. Okay, so basically in remorse for letting the lion get killed in the first place, because Hera was the one who sort of forced Hercules out on all of these 12 trials, Hera then positioned the lion to live up among the stars. Now the lion, the figure of the lion, was also of significant importance to the Egyptians. Cats were much more important to the Egyptians, one of the things I have in common with Egyptians. In ancient Egypt, the constellation was aligned, that we call Leo, was aligned to the summer solstice. The Regulus star, which is a bright red star, was actually thought to be providing some of the extra heat that was found during that time of year. When Regulus is up during the day, the temperature goes up. So it must be that this star is adding more heat to the Earth's atmosphere. Not exactly correct, but what the heck. The rise of the constellation coincided with the flooding of the Nile. Egyptians depended totally upon the Nile for their survival. So in this hot period of time when Regulus is up before the floods, the lions also came from the plains to the banks of the Nile. So the arrival of the lions along the banks of the Nile was seen as an indicator that the floods were going to arrive very shortly, which is going to allow the Egyptians to continue their cycle of life based about agriculture along the Nile. So since the Egyptians were so dependent upon the lions as simply foretelling the arrival of the rainy season, they effectively almost worshiped the lions. Again, not as much as cats, but they did have a great deal of respect for the lion. Just as a total aside, the poet Ovid, about 40 BC, wrote a story of Paramus and Thisbe in his poem Metamorphoses, which you might have heard of or even have been forced to, I didn't say that, to read in your high school days. They were two teenagers in Babylon. Because of their family rivalries, their parents refused to allow them to have contact with each other, but there's a crack in the wall between the houses. They can talk to each other. They make a plan to meet by a mulberry bush with white berries. Hopefully you see what direction this is going in. Thisbe arrives first, encountered a lion, bloody from its latest meal. Frightened, she runs off, losing her veil in the process, which the lion picked up. So the blood that was on the lion's mouth from his previous meal ends up on the veil. Lion was not overly impressed with the veil, so he just moved on. Paramus arrives a little bit later. It's his fault for being late. He sees the bloody veil, assumes that Thisbe has been killed by a beast, the lion or whatever. At this point, of course, his 13-year-old life is no longer worth living, so he falls on his sword, coating the mulberry bush in blood. And then Thisbe returns, finds Paramus dead, sings the appropriate songs of lament, takes the sword, and does herself in the same way. So now you know why the fruit of the mulberry is now red, and you know where Shakespeare didn't really dream all of this stuff up on his own. He had a little bit of help. So that is a little bit about Leo. And I will now move on to our next object, which is the bright star Regulus. As the brightest star in the constellation of Leo, it also has the Alpha designation, so Regulus is also Alpha Leonis. Here are the RA and DEC for Regulus. Fortunately, it is very definitely something you'll be able to just look up and see with your eyes. A little bit about Regulus. The name stands for Little King, also Heart of the Lion. Must be two different languages. Regulus is actually a quadruple star system, so it's actually two pairs of two stars. The primary star is about a magnitude of 1.4 and is the 25th brightest star in the sky. The whole grouping of the whole quadruple system is closer to a magnitude of about 1.35, which would make it about the 21st brightest, if we think of it just as being one star, which is what it looks like to our eyes. The primary star is a spectroscopic binary, which has never been observed, but is most investigations lead to the conclusion that is most probably a white dwarf. The other two stars are somewhat separable, but that should be an 8.1, not 8.1. The B star is somewhat visible, readily seen in telescopes. The C star at a magnitude of 13.5 is going to be a bit more difficult to see. Regulus is also part of a couple of different asterisms, one referred to as the Four Horsemen of the Apocalypse. The other, more importantly to the observing we typically do, it's part of the spring triangle with Spica and Arcturus. Okay. So the next object I wanted to talk about was, again, a classic galaxy. Going to talk about a couple of galaxies because this is a wonderful time of year to be looking at galaxies in the sky. This is Messier Object 104 or NGC 40. Sorry, I can't read that under my little name tag here. Also referred to as the Sombrero Galaxy, and you can see from looking at this image why it has that particular name. This particular image was taken by the Discovery Channel telescope in May of 2012 up at Fort Lowell. And again, it's a sort of the classic type image of the Sombrero Galaxy. This is looking at the Sombrero, looking at in the infrared wavelengths. So astronomical infrared can be anywhere from like 1 micron, typically out to about 3 microns. Typically, we don't do observing astronomy in the 8 to 12 micron regions, but it's sort of, we can see a lot of energy, if you will, in that band around the outside, and you can still see the central core there where there's a black hole. But the infrared energy here indicates that there's still a lot of activity going on in this galaxy. And here is another picture, and this is not something you're going to see with your backyard telescope or even any one particular telescope. This is a mosaic compilation from the Hubble, but it just shows such beautiful detail, especially of all of these gas dust lanes. And remember, this was the region we saw highlighted in the infrared photographs. There's a lot of residual gas material here, which is how new stars get born. Absolutely beautiful picture. I hope you can see it. I know you can't see it in as fine a detail as I see here, but it's an absolutely gorgeous image. So a little bit about the Sombrero Galaxy. It's a spiral galaxy, somewhat like the Milky Way, but we're looking at it edge on, so we can't sort of see the arms. We can very readily see that bulge in the center. It has about 2,000 globular clusters within the region of the galaxy, which is a good number, but it's also a long distance away. The radio emissions indicate that it does indeed have a very large central black hole. The material is still being collected within that region, but right now it's already up to about 1 billion solar a billion solar masses. The total mass of the system is about 5 billion times that of our sun. It's about 28 million light years away. No, it's not. Yeah, 28 million light years. Yeah, okay. I didn't put the zeros. I put an M instead. nearly confused myself there. Visible magnitude is about an 8. It's a telescope object, but it's going to be very beautiful to take a look at. You will see, not obviously not the Hubble type detail, but you will see some effect of some structure. Parent dimension is about 8.7 by about 3.5. Again, it's a nice sized galaxy in your telescope. Spitzer Space Telescope determined that there was a spiral galaxy inside of it, so it may have been reclassified as elliptical, but most of the references I have still indicate that it's considered to be a spiral. So active investigation is always fun. But again, definitely one worth looking at. One that's also very much worth looking at is Messier Object 101. This is another spiral type galaxy. And in this one is sort of more face on, so we can clearly see the arms of the spiral, but they're sort of asymmetric, wider, narrower. So it's not the nice classic picture, but it absolutely is a beautiful object to take a look at. And you're not going to see this with the eye, but you can image it with an amateur telescope and still see quite a bit of the structure, including some of the very obvious asymmetry and the central core area as well. This is referred to as the Pinwheel Galaxy, and it does look like those little toys we played with in our younger days. Visual brightness is about 7.9. Again, you're going to pretty much need a telescope to see anything. I need to go back to putting the M's there. So 21 million light years away. Apparent dimension is about 22 arc minutes. Absolute brightness, so if you were parsec away, it would be about a minus 21.6. In other words, it would be pretty bright if we were a lot closer to it. This is about a luminosity of about 30 trillion times that of the sun. And I believe I forgot to put the word mass right here. So the mass is about 1 trillion times that of our sun. Okay. Actual diameter is about 170,000 light years, which is noticeably larger than the Milky Way. Again, very, very asymmetric. And it's one of 9 members of the local galaxy group. So Messier Object 44 or NGC 2632. Again, the RA and DEC coordinates are here for those of you who want them. It's located in Cancer. It's also referred to as the Beehive Cluster. If your skies are dark enough, you're going to be able to look up, and if you know where to look, you're going to be able to look up and almost see sort of this a fuzziness due to this concentration of stars. And we can see from looking at the image that, yes, there are some red giant type stars, but mostly we have hot, bright, youngish type stars, which is matched up by some of the history we know of or science we know of M44. It's about 600 light years away, obviously relatively close. That's where open clusters are. And it's only about 600 million years old compared to the billions of years for the universe as a whole and the 5 billion years for our particular galaxy. Visual magnitude, 3.7. Diameter is about 15 light years, which is about 1.5 degrees as we look at it. So about 3 times the size of the moon if you were to put it in your telescope or look at it with your eyes. About 1,000 stars, but the total mass is only about 600 times the sun. So there are going to be, although there are some massive stars, most of them are scale of our sun or smaller. Interesting bit of information is that this open cluster has a lot in common with the movement and metallicity and other properties of the Hyades star cluster. So they were probably formed from the same gas cloud at slightly different periods of time. Another pieces, a couple of interesting pieces about M44. Again, I said you are going to be able to, if you know where you're looking at, find it. Of all of the Messier objects, only the Pleiades, M45, is closer, and only M45 and M31 are any brighter. So definitely a Messier object worth taking a look at. And again, when you look at it through a telescope and you just see all of those stars clustered together, I love that effect of seeing all the bright stars against the dark background. It's, again, a very beautiful cluster to look at. Not quite a globular, but sometimes it's nice to see the individual stars. And keeping with May's request to keep it short, that's all there is for tonight. So thank you all very much.
Oh, thank you, Mary. I'm so sorry to ask you to shorten it.
No, don't worry about it. Dolores's talk was wonderful.
Yes, well, both of your talks were wonderful. We have a question. Let's see, from Doug, who asked about the luminosity being 39 billion. I think this was the object before M44 that he's talking about.
Okay. Let me go back.
Yeah, I'm sorry, I missed the question until after we were through with that, the object he was talking about, but.
I could have sworn I double checked all those numbers today. Okay, the mass. Yeah. Uh-huh. Yeah, I believe it was 1 trillion. But I was surprised when I read that number myself. I will go and double check it, but yes.
Okay, and that was for which object?
I believe it was 101.
Okay. Thank you, Mary. So there's a comment of 30 billion. You said 30 billion, but the slide says, oh, 30 trillion, but the slide says 30 billion.
Okay, yeah, it's 30 billion. The luminosity is 30 billion suns with a mass of 1 trillion suns. So the line under that was, yeah. So the luminosity is 30 billion, but the mass, which is the number right underneath it, but I forgot to put the mass, is 1 trillion. I knew I had a trillion in there. And yeah, so underneath luminosity, there's the number 1 trillion. That's the solar masses.
Okay. Thank you, Mary. Okay, any other questions? I don't see any at this point. Okay, well, Mary, it looks like unless we have any Facebook questions, do we have a Facebook question, Jim?
No, nothing on Facebook.
Okay, thank you. So our next item is that Jim Knoll is going to make an announcement.
Yeah, and this is good for not only our members, but also our folks that are on Facebook. I'm actually going to talk about 2 star parties that we're going to stream to Facebook and YouTube coming up in the next 2 weeks. The first one is on April 10th. We are going to stream a star party from Oracle State Park. It'll be several of the TAAA telescopes, but there's also going to be a talk by John Barentine of the International Dark Sky Association, and some music, a couple of just a short song or 2 of music. So that's going to stream to the TAAA Facebook page and YouTube channel on April 10th. So that's next Saturday, starting at 7 p.m. Now, for any of you that are not in Arizona, Arizona does not do daylight savings time. So 7 p.m. is Mountain Standard Time, which for everybody on daylight savings time would be the same as Pacific Daylight Time. So that's next weekend. And then the following weekend, we're going to have a huge, wonderful presentation that's going to be great for the entire family. It's our Astronomy Festival, and we do that annually. And we usually try to do it in person in Tucson so that we can interact with people coming to the event. But we're going to be doing this one virtually. And this one will be April 17th. And it's going to be about 4.5 hours long. So you can watch the entire thing. You can join us for any part of it. You can watch it later if you want to. It'll be recorded. It'll go from 3 in the afternoon until about 7:30 or so. It'll be aired to our Facebook page. So right where you're watching, for those of you on Facebook, and on our YouTube channel. And they'll be aired as a premiere. So you should see them even several days in advance. You'll see it come up on both of our social media platforms, and you can click on it and follow it and things like that. What we're going to be doing is we're going to do some solar observing. We're going to have some activities that'll be good for the entire family, all different kinds of level. We're going to have one of our members do a guided walk around the night sky, talking about ancient and Native American star lore. We're going to finish up with an evening star party. So again, that one is April 17th, starting at 3 p.m. Arizona time and going till about 7:30. All right, thank you very much.
Great, thank you, Jim. And I hope people can join you for that, because we get such wonderful feedback on these events. So we have lots of volunteers involved in this, and so it will be wonderful if people can attend. Next, we have David Levy for our monthly poem.
Well, thank you very much, May. And I wanted to add my expression of enjoyment for both of the presentations tonight. Dolores did a wonderful presentation, and I think that if Shakespeare could come back for just a moment, he would rush to our TAAA meeting and add his congratulations, because I think if Shakespeare were writing today, he'd probably write about asteroid Bennu. Mary's talk actually specifically mentioned Shakespeare at one point, and I was really glad to hear that. And my quote for the month is from Shakespeare's Romeo and Juliet. And this passage is in pieces on the moon right now as a memorial to Gene Shoemaker, who founded the science of astrogeology and did so much else to contribute to our search for understanding and knowledge. It goes like this: come, gentle night. 3 very, very special words to begin this. Come, gentle night. Come, loving, black-browed night. Give me my Romeo. And when he shall die, take him and cut him out in little stars. And he will make the face of heaven so fine that all the world will be in love with night and pay no worship to the garish sun. Thank you, May, and back to you.
Thank you so much, David. That was a beautiful item to contribute. Thank you. At this point, we're going to say goodbye for this evening to our Facebook people. Thank you so much for joining us. We hope that you'll look at our webpage. We have lots of information on our webpage that you might enjoy, and you can learn more about astronomy. And we also hope that you'll join us in the future, the first Friday of the month, or on any of our events on YouTube and Facebook. And as Jim mentioned, there's these upcoming events, but we also have other items on YouTube and Facebook from the past. So thank you so much for joining us, and we hope to see you in the future.